Let's dive straight into one of the most misunderstood areas in Cambridge physics. I'm talking about a place where a really popular graphical shortcut is, quite frankly, actively destroying exam scores. You know the drill, right? You look at the equations of motion, you see a shape on a graph, plug in a number, and think you're good. Well, you're in for a pretty serious wake-up call. Today in this explainer, we're completely tearing down the myths surrounding the area under a velocity time graph and the gradient of those ST and VT graphs. So many students rely on this quick visual trick to find the area under a VT graph or the gradient of ST and VT graphs. But here's the thing. This exact shortcut is risking your grade boundaries right now. You look at the curve, you spot a triangle, you punch a quick calculation into your calculator and write down the answer. Boom, done. And yeah, it feels fast, right? But honestly, it's a massive trap. Sure, skipping the procedural steps might save you 30 seconds, but it's going to cost you the lion's share of the marks. Now, if you're sitting for the Cambridge AS and A-Level Physics Syllabus 9702, regular, ordinary revision of kinematic equations simply will not save you here. The examiners, well, they aren't just checking to see if your calculator has batteries. They are looking for the actual conceptual wiring in your brain. The syllabus explicitly states that top-performing candidates have to be able to transfer this conceptual understanding to totally unfamiliar contexts. So, rote memorization of a shortcut? Yeah, that won't cut it when the scenario shifts unexpectedly on exam day.
All right, let's move into Section 1, the method mark strategy.
Instead of panicking over these complex multi-stage kinematics questions, we need to really understand how marks are actually awarded. Examiners are basically acting like detectives, tracing your process. They're testing distinct cognitive domains like application and analysis, not just raw knowledge. So when they ask you to analyze the gradient of an ST graph to find velocity or the area of a VT graph to find displacement, that final number, it's literally just the tip of the iceberg. The method marks are awarded for the invisible architecture beneath your answer. It's about explicitly demonstrating exactly how you got there. To absolutely nail these method marks on tricky past paper problems, you've got to follow this exact 4-step procedural framework every single time. First, step 1, you identify the underlying concept. Then, step 2, extract the evidence or data straight from the texts and tables they give you. Step 3, apply your scientific reasoning to show those causal relationships. And finally, step 4, present the whole thing using precise examiner wording. Seriously, skipping even one of these steps is like leaving the front door to your grade wide open. Which brings us to Section 2, flawed versus top band answers. Let's look at this comparison. That flawed answer on the left, it's basically a numerical jump scare. It's just a random number thrown onto the page, totally missing appropriate formats, units, and clear annotation. But then, look at the top band answer on the right. It perfectly extracts data from the graph. It uses strict conventions like proper headings, and it displays the correct terminology. The right side tells the examiner a complete, logical scientific story, whereas the left side just kind of shouts a random ending at them. Now, under time pressure, your brain is naturally going to want to panic and skip these vital steps. To fight this, I want you to create a simple, kind of weird mnemonic right now, using the first letters of your key physics terms. Whether it's to remember the steps of data interpretation or the specific requirements for graphical presentation, a quick, funny memory hack acts like a mental parachute when you're suddenly staring down a complex VT or ST graph on the exam page. Moving on to Section 3, the top 3 examiner warnings. Let's look directly at the principal examiner reports. These are an absolute goldmine, showing exactly where thousands of students bleed marks year after year. Number 1, students constantly confuse cause and effect in graphical methods, mixing up what the gradient actually represents versus the area under the curve. Number 2, they neglect proper headings, format checks, and clear annotation on their workings. And number 3, they give generic answers that might sound smart, but totally fail to link the scientific reasoning back to the actual scenario in the question. I really want you to burn this direct examiner quote right into your memory. Context specificity is the ultimate key to unlocking top marks in data interpretation. Think about it. If the question is about a parachutist falling, your analysis of the velocity time graph cannot just talk about generic objects in motion. No way. You absolutely must explicitly link your evidence-based conclusions to the air resistance and the acceleration of that specific parachutist. That leads us straight into Section 4, deconstruct, solve, and evaluate. To completely bulletproof your answers against those common examiner warnings we just talked about, you need a timeline. First, right at 0 minutes, you deconstruct the question to extract the relevant data. Then, You select your analytical framework, basically deciding if you need the area or the gradient. Next, you execute the calculation systematically with crystal clear notation, and finally, you present your final answer using correct terminology and check it for reasonableness. This timeline is your absolute safety net, guys. Furthermore, that final step, evaluating evidence quality, means you have to systematically identify limitations and assumptions. For example, when you calculate the distance from a VT graph, what assumptions did you actually make about the initial acceleration? Are there alternative interpretations of the data curve? Determining how these limitations affect your final conclusions is exactly what elevates your answer from just standard application to high-level critical analysis. And finally, Section 5, the final strategy loop. So we've systematically dismantled the dangerous shortcuts. We know that jumping straight to a numerical answer on an ST or VT graph is going to rob you of your method marks, and we've built a new high-mark analytical framework centered on process, context, and clear annotation. But that leaves one massive, unresolved question hanging in the air. If the popular trick is a trap, what exactly is the safe, examiner-approved shortcut? How do you tackle these common traps without running out of time in the exam hall? Well, to discover that exact safe shortcut and to see how it perfectly applies to evaluate and calculate questions without sacrificing a single method mark, you must subscribe to our YouTube channel Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. But before we wrap up this explainer, I'll leave you with this question to ponder today. If a simple visual trick has been silently costing thousands of students their top grades every single year, what other shortcuts in your revision are actually slowing you down? Keep analyzing, keep questioning, and never fall for the shortcut trap again.